So I don't know why I was very sensitive when I was younger to find those ones they cheat, but as I said, nowadays I don't care at all. I don't care. And we had a professor in Ohio State, I think I told you about the copying, once me and another lady. He was exactly the same. He was Russian, he was I love him, He was a really good professor, and he made that. And let me tell you a story about, his exam, final exam he had. We had a sliding mode control with him, and he was a very smart guy. His solutions are very, very short. He gave you the exam, and it was all available. If you have a good network, especially in electrical engineering with Chinese and Indian people. I'm not saying, well, I have lots of good Chinese and Indian friends. All the exams are there. You know what I'm saying? And I had a copy of most of exams. Previous exams. And he's the guy who doesn't care. At some point I was thinking why he doesn't come with a new question. Now I know why he doesn't come with a new question. He just said it be the same question, and the solution is there. His solutions are pretty smart solutions. For example, in 3 lines you get the answer. The way I like to solve it, I want to go. That was more like mechanical operation, about control system, those kind. I write everything. Mine end up being like 1 page. But I love it that way because I understand mine. And we had the question. We went to the exam, final exam. Some people, they were really rude. They wrote the exam with them, and they were copying it in the exam. I really felt bad. But I said, okay, I'm gonna do my way. And I made one mistake. In one of my solutions, I made one mistake. He gave me A+. Those ones they copied. As soon as they leave one dot, he gave them either A- or B+, something like that. He was extremely tough on them. As soon as you make a small mistake, something you usually don't care, bring it to B+. That was the way he punished them, for that, And as I said, I made a mistake, but my solution was a small mistake, but in the middle of the question. I went all the way to the end with my way, not copying his paper, And he gave me A+. He didn't consider that. That person taught me a lot, I figured out later, especially in the graduate level, exams are meaningless. You want to research, you want to publish paper, you want to do your PhD, you want to learn as much as you can. That's the main goal to do. If you don't want that, that's fine. That's fine. And I think if somebody wants to hire you, if you say I got a B+, or I got a A-, or I got an A+, or an electric machine, something related, I think they said all the are good. All the are good. Let's talk a little bit about how much you know about this one. They put 3 candidates here. Talk to them. One got an A+ with cheating, one got a B- with not cheating. Believe me, the B- is going to get the job because as soon as they ask you 3 questions, they know who you are, and actually it makes it a little bit kind of sensitive. You are A+, and I ask you a basic question, and you cannot answer it. How this guy got A+? And he doesn't know this basic question. It just tricks something. Inside your mind. Something is wrong. A+ and cannot answer a basic question. But this is not about the email I received, but in general, guys, try to learn as much as you can. If you want to cheat, at least do the cheat, wisely. Go read the answers. Don't copy. Don't be a copy machine. And but also I guess you do not do that. Up to you guys, whatever you want. Okay, we'll go continue on the. Let me see what the last topic we covered. I think we went to the power angle characteristic. We finished that one, I believe. And we talked a little bit about the this is the last one. Oh yeah, we did calculate. We went through the synchronous machine test. We calculated the SC. So let's continue this. There are 3 more topics we want to cover on the synchronous machine. Tuesday we don't have a class. So keep in mind, Tuesday we don't have a class, and I want to first talk about the paralleling, synchronous machine. machine, because that's a very, very common topic, you know. That one, it happens a lot, you know. The paralleling synchronous machine, why do parallel synchronous machines? Why do parallel sources, you know? You know why? We parallel, for example, 5 sources together. 5 batteries. Why do you parallel them like this?
So one runs out.
For example, you have one battery here, you put 5 of them here, or 2, and you make it parallel, 1.
So if one goes out, at least the others are running, even if you're not at full load or whatever.
Yeah, that's 100% correct, but the first thing they say, that's more capacity, more power, you know. So for example, this one give me, I don't know, 10 watts, this one can give me 10 watts, I can have to put it together 20 watts. But he's completely correct. It gives you reliability. If you have a, for example, you want to use 20 watts, you know, you put another one here, you have a 30 watt, if something happens to this one, you can rotate, right? You have it reserved, you know. That's another thing, you parallel them. Higher power, reserved in the system, you will have some reserve in the system, and they do it for all the sources now. Now synchronous machine, to make them parallel, let me ask you very, very simple. If you have 2 batteries, ideal, and they have a load here, and they have a load here. What condition this battery has to be to parallel them? So they should have the same voltage and whatever. No, capacity is how much energy they have. But if you are saying voltage,
Ends must be connected. The ends must be connected to each other.
well,
Like the ends, like the positive need to be together.
not the end. You know, the polarity should be the same, right? So you have this one. You cannot do the other one like this, you know, right?
Yeah.
So the polarity should be the same, right? Positive to positive, negative to negative, and they should have same voltage. Very simple. For the DC sources, if you have a DC generator, the same thing. You have a 2 generator, you want to make them parallel, right? I have a 2 generator, I don't care what they are. On the excitation, if I'm going to make this one parallel with this one, here will be the output. I should make sure this voltage is equal to this voltage, and if this one is positive, here is negative, this one should be positive, here negative, right? Same polarity, connected together, and they should have same voltage, right? Now tell me about the 2 AC system, 2 single phase source. AC single source. And what else? Magnitude should be the same, right? If you have 120 volt, you cannot connect it to 540 volt, right? I thought that you said the one they come a little bit later. If the first one comes to mind, I think it's magnitude, right? You say, they have to be the same magnitude, right? You cannot connect the 10 volt to 20 volt, right? And the next one comes to mind is frequency, usually. You say, okay, yeah, so they should be the same, because if they are not, it's going to be kind of messed up. The third one is they should have the same phase, right? Because if this one is 1, right? If the second one is not exactly like this, for example, it's like this, again, we're going to be in trouble, right? Because at this point, at this time, this one is this much, this one is this much, right? We have a big voltage difference, right? So for single phase system, magnitude, frequency, and phase, right? Now tell me what the 3-phase system. Same thing. And what else? And what else?
The direction, the rotation.
See, he's trying to say right thing, but the word he's using is not correct. Sequence. Sequence, right? It's the rotation. It should be ABC. Most of them, they should be ABC or ACB, right? Remember from power system, we said we can have an ABC, right? Or we can have an ACB, right? Basically, one is rotating this way, one is rotating this way, right? Most of them, they should be ABC or ACB, right? Because, again, even if you connect the ACB to ABC, it's a disaster. It's going to cause a huge, huge, huge problem, right? So, for AC sources to parallel them, 3-phase AC source. First, paralleling, you know, the title, I know you were going to ask, that's a paralleling synchronous machine. Paralleling synchronous machine. Actually, we should say synchronous generator. Because loads usually they parallel sources, not loads. Loads they can connect, at any time they can connect to the system. So before getting to this one, let's do it this way. Let's go through the conditions for paralleling two three-phase AC source. First, same magnitude, right? Second, same frequency. Third, same phase. Fourth, same sequence. So these four conditions should be, we should have these four conditions to be able to parallel. Before getting to the detail of paralleling, calculation, those kind of things, let's say we have a two synchronous generator, G1, and we have a G2. This is single line diagram. Basically this is a three-phase system, just I'm drawing one line here. And we have a load here. We want to parallel this first before, or other things. This is maybe not common. The other things common is this. You have your grid here, right? This is a utility grid you have here. You have one power plant. It's going to bring a generator to the system. This one needs to connect to this grid, right? Grid is basically like an ideal source, right? Almost like an ideal source. Is another generator. It's not rotating, but it's another three-phase system sitting there with some frequency, right? Now the new generator is going to connect to the grid, right? So basically it's going to be like this. The other one will be like this. So for example, we have a generator here, and here there is an infinite bus, for example, and here is a VT with 0, and we have a load here, and we have a load here. Basically, before this generator coming in, this grid is supporting this one and is supporting this load, right? Now we're going to bring this generator in, right? Basically, this generator has become parallel with this existing grid, which is another source, right? So all these conditions should be okay. You say, first of all, the grid is 480 volts. Make sure this one is 480 volt too, right? A little bit difference is okay. For example, let's say grid is 480 volt. You are for, 75 volts is not a big deal because at the end of the day, if you look at it, this is the 475 over the square root of 3, right? You have an XS here, right? Let's forget even R, right? You have an XS here, and you have a 480 over the square root of 3, right? You're going to have the small current going this way. But if this one was not here, you have to have perfect voltage, perfect match, right? Because even 5 volts divided by 0 is going to be infinite current, right? But because we have this impedance here, a little bit mismatch is okay. But if the mismatch is big, it's going to be a big issue, right? You're going to see huge current going through the system. Now, so we'll make sure, say, oh, the grid is 480 volts. So let's say the generator is rotating at synchronous speed. Just asking this question. For example, this grid was 480 volts, right? This generator is working at, for example, line to line that we were talking. So this is 400 volts, for example, and it's rotating at synchronous speed. And this grid is 60 hertz, for example, right? So basically, this one is going to be, when it's rotating at synchronous speed, it's going to guarantee synchronous speed of 60 hertz, right? It's going to guarantee the voltage generated here is how much? 60 hertz, right? For example, if the machine is a two-pole machine, right? Let's say two-pole machine, it's going to be NS, it's going to be 120F over T, right? So basically, if we are 60 hertz, is 120 times 60 over 2, is that how much? 360, right? Basically, you can look at the generator speed and say, hey, I'm good. 360 RPM means I'm 60 hertz. So I'm frequency-wise, I'm good with the grid, right? Now you're 400 volts. Oh, not good. What should I do? Well, I'm not good, right? I cannot connect, it will be different, so you're like 80 volt different.
You can increase the flux.
Okay. So he said increase the flux. How to do that?
Field current.
Yeah, I need to increase my field current, right? IF. If I increase my IF, EAF is going to increase, right? Basically, this voltage is going to go up, right? So basically, you adjust your excitation system to get the voltage you want, right? The speed is the synchronous speed. I can increase the speed also, right? You remember? It was proportional to IF times omega, right? To increase the EAF, either I can increase it or I can increase this one, right? But omega I cannot change it because I have to match this frequency, right? I have to give it on 3600 RPM to have 60 Hertz. I cannot go more. Yes, if I go higher, my voltage also is going to go up, but the problem is my frequency is not going to be the same, right? So I cannot touch my frequency because I need to match my grid, right? Now, the only other way I can go up is to increase flux or IF. If I increase flux or IF, the voltage is going to go up, right? Now, let's say we adjust this one. We look at the frequency, okay, we are good. We set the excitation system, we are good. Now, phase sequence also is something you have to, know which one is A, which one is B, which one is C. Easily you can find out that one, If you put them on the scope, you can see this is A, this is a B, this is a C, right? But the fourth one, same phase, I want to talk about. So these three, you will check. Same sequence, Same sequence, you can quickly check it, right? With the scope, you can check all this kind of things. But the fourth one, same phase, you are going to do that. This is an old method. There was equipment in all the power plants. They call it synchronoscope. Synchronoscope is a machine. It still is there because it will tell you if you are at the time you can close this switch or not. And lots of them they are automatic. As soon as it's there, boom, it's going to close the switch. But I want to tell you how it does work. Synchronoscope. These days, I'll talk about inverters, and after I finish this, I'll tell you how we do this thing. But it's the old things, and it's still in all the power plant, all the generator, they use synchronoscope, to connect this one. When we had it, I don't think so you guys have this lab here, but when I used to have my electric machinery course, we call it electric machinery, not the energy conversion, we had a lab to connect the generator to the grid, There were two ways to check the third one, to make sure you're in the same phase. Let's put it here. This is the phase A, right? Let me see, this is 90. Phase B is going to be here. And phase C is going to be, I think that is somewhere. Where's the B? It's the 180. 180 and it's a 270, 240, somewhere here, I think. This is the A, B, C. Let's call it A1, B1, C1. Right? Now, the second phase, the second source, this could be the grid, this one, and the second source we have, let's put it here. I'm going to put it in the same phase and in the same order. Let me see here. This is the A2, B2,